Welcome to the second presentation of today's seminar. Our second speaker today is Auguste Bourgois, and he's a third-year student, PhD student at the ENSTA Bretagne. And yeah, he's working like our first speaker today in the field of underwater robotics, and particularly he's working on localization and verification. And yes, he's doing his PhD work together with a company that's 4C Robotics in Paris in France. And yeah, today we'll get a very interesting presentation, hopefully, in the frame of stability analysis of stochastic filtering approaches using the extended Kalman filter technique. Okay, we're looking forward to your presentation, Auguste.
Well, thank you. Good afternoon, everybody. I will stop my video and start it again for the questions so that I don't take all the bandwidth. My talk today will be about set membership methods for verifying stability of dynamical systems, and in particular Kalman filters. So I'll start by introducing the context of, let's say, my thesis, but also this talk. Then I will continue with general reminders about stability of dynamical systems, in particular discrete time ones. And then I will apply the theorems and definitions I've been presenting in this second part and the third part to prove stability of a localization system based on a Kalman filter. Right. So quickly for the context, my thesis, the goal of my thesis was to explore the methods that can be used to dock an AUV inside a docking station. So this is looked into right now by many offshore companies, because with the increase of in the numbers of offshore wind farms, we need autonomous robots that can inspect them while being able to recharge, for example, in a docking station, or be deployed autonomously from USV and be recovered autonomously. So that means we have a docking maneuver to perform, whether it's on a docking station or on a USV. Yes, so that means we have to perform a docking maneuver, just as it's represented by this picture that has been taken during one of our sea trial in the south of France, sea trial done by 4C Robotics, which is the company that funded my PhD. So to perform this docking maneuver, we use state-of-the-art control and localization techniques. So I represented here on this diagram the general software architecture of our robot. So the robot is represented by this big rectangle here. We can see that the robot is interacting with both the environment and the user. So the user gives instructions to the robot, such as a mission like explore this wind farm and come back to your station when you're done. And the robot, by means of sensors and a few algorithms, so a state estimation algorithm, say a Kalman filter, for example, a control algorithm, mission planning algorithm, and a few motors, the robot follows the mission that has been input by the user and hopefully performs it correctly. So in this thesis, I didn't develop new methods to perform docking maneuver because they already exist. They are like used quite a lot in the industry and they work pretty well. What I did instead is what I wanted to do is to develop a method that can prove a priori that the mission is going to work, that the robot is able to perform the mission without any problems. That means in our case that the robot will be able to reach its station and dock inside it. So to do that, I needed to model the robot, its environment, and its target as a dynamical system, and model the docking mission as a stability problem. So I explain here why on this picture. Let's say that the point D here is the docking station of the robot. Then we want to prove that we want to find the initial conditions, so the initial positions of the robot for which the latter will be able to go back to the point D. So we can see on this picture that, for example, if you take into account the controller, the localization algorithm, etc. of the robot, if the latter is initialized at point x1 to x5, it will be able to go back to the point D, whereas if it's starting at x6 or x7, it won't be able to go back to point D. And this is basically a stability problem because we can see that the robot, when initialized at the points on the right of this picture, will converge towards the point D. So this is why we choose to model it as a stability problem. And this in the aim of proving a priori that the mission is feasible. Okay, so let's talk now about stability of discrete time systems. Quick reminder on discrete time systems. So a discrete dynamical system is, mathematically speaking, simply a function that maps the state into another state by a discrete jump in time. So this is why we can express a discrete time dynamical system as mathematical sequence, such as this one. Let's now talk about uncertain systems. So let's consider that we have a robot that is modeled by this system. So of course, a robot can be modeled in a much more complex way using, for example, hybrid models. But here we will consider that we model our robot by a discrete time system of this form. Then we have to take into account uncertainties. The uncertainties can come from the initial state of the robot that is not perfectly known, can also come from uncertainties in the evolution function that models the dynamics of the robot. So say, for example, the mass of the robot is not perfectly known, then we have an uncertainty, etc., etc. All the parameters can be represented as can be like uncertain and therefore represented as intervals that I will introduce a bit later in this talk. Right now, actually. So an interval is a connected subset of R. And from intervals, we can build boxes, interval vectors, thanks to which we can represent the state of a robot. So this is usually what we do in underwater robotics when we use intervals to represent uncertainties. We have here a robot, and then its position can be represented as a box in 3 dimension. Of course, the state of a robot can be much bigger than 3 dimension, but then that means we have a box in Rn. That being said, we have seen that the robot is modeled by a discrete time system that involves a function f. So we need a way to enclose the image of an interval inside a box. And for that, we use what we call inclusion functions. So we have different types of inclusion function are represented here. So on the left, the let's say the initial box of the system, the initial condition, and on the right, the yellow blobs represent the image by f of all the points inside X. We have, as I said before, different types of inclusion function. The blue square is a general inclusion function. One specific one is called the minimal inclusion function. It's represented here by the green box, and it's actually the smallest box that encloses the image of the set X by the function f. So usually we cannot find mathematical expression for the minimal inclusion function when the function is strongly nonlinear. So for that, we will use what we call the centered form, which is a way of building an inclusion function that will be tending towards the minimal inclusion function if the box, the state of the robot that is enclosed in the box X, is small enough, meaning it's the width of the box is small enough. And so here I recall the expression of the centered form. And as I said, the centered form is an inclusion function for f. Right. So why do we do that? Why do we use the centered form? Because as I said, if the width of the box here is small enough, then we have, compared to let's say natural inclusion function represented in red here, we have a smaller enclosure for the image of the images of the set XA. If the box is too big, then the centered form is not performing as well. So that's why we want small boxes in the first place. Right, so let's now talk about stability of discrete time systems. We will, of course, make use of what I've been presenting before. So a quick reminder about stability and the definition of stability of a discrete time system. So consider we have this system here with a fixed point x bar. Then the system is stable around x bar if we can find the neighborhood delta such that the system remains in a neighborhood epsilon of the fixed point of the system. We can also introduce the definition of asymptotic stability, which means that the system is going to converge if it is initialized in a neighborhood delta, and if the system is going to converge towards the fixed point of the system. So this is a more interesting definition, especially for our problem, because if we can prove that our robot is asymptotically stable around, say, its docking station, then that means it will converge towards its docking station and actually reach it. Right. So how can we prove stability of uncertain discrete time systems? Before I was talking about only discrete time systems. Now let's talk about uncertain discrete time systems. So some methods do exist. For example, a method based on the jury criterion, or a method checking the eigenvalues of the system. Unfortunately, these do not provide the designer of the robot with stability neighborhoods delta and epsilons I've been talking about earlier. And these neighborhoods are very important for a designer, because the designer of the robot wants to know that if he or she launches the robot in the water, the robot will actually be able to dock back on its docking station. And for that, we want to prove that if the robot is initialized in a certain area, it will be able to converge towards a certain point. Right. So during my thesis, I mean, we developed a method based on stability contractors. So this is a new concept we introduced. So quick reminder about contractors. Contractor is an operator that takes a box as an input and will contract the box, meaning making it smaller, by removing points inside the box that do not, I mean, that do violate the constraint that is associated to the contractor. And so what we did is create a stability contractor. That means if we feed the contractor with a box x0, we are sure that the box x0 will be contracted, and the remaining solutions of that are inside x0 may um, may lead the system towards its fixed point. So this is the definition of a stability contractor, simple one, as we consider in this definition that the fixed point is always zero. Of course, this can be extended to fixed point like different than zero, but we'll keep the problem simple for the moment. So we basically, these two equations are the basic definition of a contractor, and the two other equations actually implement the stability constraint for the contractor. Right. So then, now that we have a stability contractor, we have introduced what it was. Let's see how we can build one. Well, in the thesis, we also have shown that the iterative form of the centered form of a function um, can be a stability contractor for a system, depending on the initial state of the system. So let's say that we have an initial box for the system that is x0. Then by performing this iterative algorithm that computes the state of the system after a few iteration by the function f, and actually the centered form of these few iterations, then we can prove that if the image by the centered form is inside the initial box x0, then the centered form is actually a stability contractor, and the system is asymptotically stable inside the neighborhood x0. So we have actually found a neighborhood x0 inside which the system is going to converge towards its fixed point. A condition didn't mention here is that this neighborhood x0 must contain the fixed point. Okay, so in the rest of this presentation, we'll mainly use this definition and this theorem to prove stability of discrete time systems. Quick illustration about the theorem I've just been presenting. Consider that the red box here is the initial state of our system. Then, by iterating a few times, maybe only one time will work, maybe we'll need more than one time, one iteration, we have shown that here the system initialized in the red box will be contained after a few iterations inside the green box. And that means, according to the theorem, that the system is actually going to converge towards its fixed point D here. And we don't need any more iteration than say k. We just need at some point to check that the green box is inside the red box to prove that the system is going to converge towards D. So it's a quick algorithm. Okay, let's now turn towards the application of these methods to Kalman filters. I will start by quickly reminding what a Kalman filter is. So a Kalman filter is usually used in robotics, as I said earlier, to estimate the state of a robot. So let's say we have a robot model here, modeled by a discrete time system like that, with input U and state X. Then we have sensors on the robot that gives us the sensor vector Y, and that are based on the state of the system X. And we also have a controller here that, thanks to the state estimation made by the Kalman filter, will output control vector U. And the control vector U and sensory data y will be fed to the Kalman filter, thanks to which the latter will be able to compute the estimation of the state. We also have a few matrices that are taken into account by the Kalman filter. First one is gamma k here, which is basically representing the accuracy of the state estimation. We also have gamma alpha and gamma beta, which represent the accuracy of the robot model, first off, and the accuracy of the sensors. These matrices must be chosen beforehand at the initialization of the Kalman filter. So the Kalman filter, I will go very quickly on the equations. But the Kalman filter operation consists in two steps. The first step is prediction. So using the robot model, we were able to predict, thanks to the control vector u, we are able to predict the next state of the system and its accuracy. And the second step is the correction. So we will take sensory measurement, sensory data into account to correct the prediction that has been made. Right. So as I said before, we must choose the matrices that that basically represent the accuracy of the robot model and the sensors carefully, and we also must choose the initial state of the Kalman filter carefully. Why? Because let's say we have this problem here. We have a robot that is localized in X, and we have two beacons, A and B, and the robot is able to perform distance measurements. Say we initialize the Kalman filter with this first estimation. Then, after a few iterations, Kalman filter will converge toward X. However, if we initialize the Kalman filter there, performing the same distance, range measurements, the Kalman filter will converge there to the point X that is symmetric with respect to the line going through A and B. So this is not what we want. We actually want the estimation of the Kalman filter to converge towards the real, the actual state of the robot. So let's now dive into the problem, which is the following. We have a robot placed in X that is not moving for simplicity. We initialize the Kalman filter in X0, and we want to show that the Kalman filter will converge, the estimation of the state made by the Kalman filter will converge towards the actual state of the robot. The robot is able to perform range measurements to two beacons, A and B, that are the range measurement function is represented here. As I said before, the robot is not moving, so the evolution function of the robot is very simple. It's the identity function with respect to the state X. Its Jacobian function is then the identity function, and we do not have an input u. For simplicity, since we do not have a prediction step, we will write the state of the Kalman filter, the estimation of the state xk, and the prediction, prediction of the accuracy jk. I'll explain later why we still use the prediction of the accuracy. So as I said before, the goal of our problem is to find a stability neighborhood delta, or let's say an interval, around this the state of the robot, the actual state of the robot, such that the estimation made by the Kalman filter of that state will converge towards the actual state. So for that, we will go through these different steps. So first off, we will need to transform the localization system, um, namely the Kalman filter, into a discrete system. Then we will need to identify a fixed point of the system. We will write it V bar. And we will need to choose the parameters and the initial state of the system as an interval V0 that contains the fixed point. So that we can then apply the stability contractor and the centered form theorem have been introduced earlier to check whether the system is stable or I mean our method can prove that a system is stable or will not conclude, meaning it cannot prove that the system is unstable. It will just prove that the system is stable. If it doesn't conclude, then that means maybe you have to take a smaller neighborhood. Right. So let's continue with the formalization. So as I said before, we have to transform the Kalman filter as a discrete time system. So let's write the state of the Kalman filter as the vector vk, which contains the estimation of the position and the components of the covariance matrix of the system. So we'll represent it here by the sigma values. Once we have this state, what we have to do is to transform all the equations that are basically the general equation for Kalman filter applied to our problem into a discrete time system. So we can do that with a computer. That is highly recommended when the state vector is large, because it's very cumbersome. But in the end, we can obtain like the general form of a discrete time system, which is vk plus 1 equals a function, call it p of vk. Question: why do we keep the prediction step for the covariance? I said we didn't have a prediction step because the robot was not moving, but still I want to keep the prediction step of the covariance. Well, we do that to add a Brownian motion to the robot, so parameterized by the gamma alpha matrix. That will allow, that will avoid the covariance matrix of the system to very quickly converge towards zero. This is not what we want. Otherwise, the robot will not, I mean, the estimation of the state will not be correct. Why? Since we're working with intervals, say we have the initial neighborhood for the estimation of the state here, represented by this box, which is centered on the actual state of the robot. And say we have the initial box for the covariance matrix represented here. Then this box will contain the origin 0. So that means that for any of the points that are in this box here, which each edge of the point represent a couple of values x hat and y hat, which in turn represent the estimation of the state. That means that we can be 100% sure that the estimation of the state is true, to say, I don't know, 50% sure that the estimation of the state is true. So that means even for these corners there, we are sure, we are like between 100% and 50% sure that the estimation is correct. So that means if we want the box here to be able to contract and then prove the stability of our system, because I remind that we want the box here to contract and be inside the initial box, that means we have to implement a way of avoiding being 100% sure, especially for the outer parts of this box. Otherwise, it will not contract. So to do that, we have a Brownian motion, which is basically noise. to the system that is parameterized by gamma alpha. And doing that, we will simply shift the initial box for the covariance matrix away from 0, and then this will allow the box of the estimated uh, position to contract, because we are not 100% sure that the estimation is correct anymore. We are, say, 75 and 25% sure. So this allows the initial box for the estimated position to contract. Right. So then what we have to do is to initialize our system. So we will, let's say we have found the fixed point of this of the system that is represented by this vector here. So we said that the let's say the actual position of the robot is 0, 0. Let's say that the fixed point of the covariance matrix is going to be sigma 0, etc., etc. Then we can build an initial neighborhood parameterized by epsilon1 and epsilon2. Values are given here. And we can also choose the covariance matrices for the model noise and the process noise and the sensor noise, chosen as written here. So we try to take values that are meaningful. It's meaningful to take, say, 1 centimeter precision for a process noise and 1 meter precision for a sensor noise. Finally, we have the beacons that are represented by these two vectors. So the values in themselves are not very interesting. What we just have to notice here is that the width of the initial neighborhood for the state of the Kalman filter is very small. As I said before, since our method is based on the centered form, we have to take a very small initial neighborhood for our method to be able to prove stability. Once we have that, we just apply once our centered form algorithm on this box, because this box is centered on 0. And we obtain this box that is, trust me, contained inside the initial box. Since we have that, that means the extended Kalman filter is stable inside the box V0 and will converge towards the fixed point of the system. That means in turn that the estimation of the state x hat will converge toward the actual state of the robot, which is what we wanted in the first place. Okay, so I'll now conclude this talk. So as we have seen, the method we proposed allows to prove stability of a discrete time system around in neighborhood of an equilibrium point, fixed point. It also allows to prove stability inside a neighborhood. So we can find a stability neighborhood for the system. And doing so, we can then approximate basins of attractions, which is actually what we want. Quick reminder, a basin of attraction is the set of initial condition that will lead the system towards its attractor, say a fixed point. However, as we have seen, our method is limited to small neighborhoods only because we use the centered form. And to approximate basins of attraction, we will need bisection algorithms to use our methods on real-life system. So it's a bit of a limitation, but at least we can provide an initial neighborhood to initialize these bisection algorithms. So when we apply our method to an extended Kalman filter, we can validate a priori the parameters of the extended Kalman filter so that the latter will converge towards the actual position of the robot. So that's interesting in a real life scenario because it's hard to parameterize a Kalman filter. So if you have a method that will tell you that your parameters will actually make the algorithm work, then that's helpful. Future prospect for our method, applying our stability proving method to a moving robot, so say a Kalman filter and dynamical system for the state that is not the identity function, and then apply our method to a hybrid system. So say, for example, a continuous time model for the robot and a discrete time system for what is contained inside the computer of the robot, so its localization algorithm and its controller. A few references that have been referenced earlier in the talk. And I am done. Thank you for your attention, and I will be glad to answer your questions now.
Yes, and many thanks from my side, Auguste, for a very interesting presentation. And let's start the discussion. Okay. I currently do not see any question.
Oh, yes, I have.
Yes. Yeah. Okay. Let's start.
I have a small question. Since your method is proposed for a fixed point, right?
Yes.
Is your method an online method or offline?
It's an offline method. It's not supposed to be run on the robot. It could, in the sense that it's lightweight, and I mean, you only have a few matrix multiplications to perform, but it's meant to validate a priori the parameters you set for your system. Could be used online, for example, if you have a very intelligent robot that want to, before starting its mission, check if it actually can perform it correctly. But right now it's not meant as such a tool.
I think it is more interesting if you extend it to not a fixed point. You can extend like EKF.
So I don't really get your question. Do you mean that?
I think the question is your assumption of a constant state.
Oh, yeah, exactly. Yeah, I mean, the assumption of the constant would clearly made to simplify the problem, but we could definitely apply that method to a non-constant state.
Yes,
Just
I
that
think
the equation will be a
easiest
bit...
way would be just define the tracking error.
Yeah, absolutely.
Here's the goal is then tracking error becoming equal to 0, and your extended state vector, I think it was called VK, would just be replaced by the evolution of the tracking error, where you have the steady state again in the origin.
Exactly.
Okay, thank you.
Yes, further questions, Stefan?
Yes, I have one. Okay, Luc has a question.
Oh, Luc wants to comment.
Who first?
Luc?
Yes, maybe after Stefan.
Okay, just a quick question is to be sure that I understand what you present. Thank you again for the presentation. It's a question back on your contractor, the stability contractor you presented. Yes, what is the purpose of this contractor? Is to prove that the dynamic is a contracting one, so that the centrid form, because you use the centrid form, if I understand well, is to use that, is to demonstrate, to show that the centrid form contract boxes. It's not, or the purpose of this contractor is to prove positive set invariance. I can try to reformulate if it is not clear.
I think I've got
okay.
So basically the goal of the stability contractor is to given an initial box for your system, prove that after a few iterations, the system will be re-entering inside its initial state and then converge towards its fixed point. So for that, you have to have a way of enclosing the state of the system along these few iterations of the stability contractor. And to do that, the easiest way is to take an inclusion function. And you don't want any inclusion function because, as we have seen, some inclusion function on this, if I go back to this slide, some inclusion function insert a lot of wrapping effect in the computations. What you want is the minimal inclusion function. So that's why we use the centered form as an inclusion function for the system, and then as a stability contractor. Because first off, it encloses the state of our system, but second off, it encloses it very sharply, especially if the initial box, the initial state of the system is small enough.
Yes, what is important in what you said, it is that it is after few iterations.
Yes, well, it really depends on the system. Sometimes, I mean, most of the time, you can reach, you can re-enter your initial box in 1 or 2 iterations. If it's not the case, the risk is that after, say, 5, 10 iterations, the wrapping effect that is also included, I mean, inserted by the centered form because it's minimal, but it's not perfect, will be making the enclosure for the state explode. So if you've reached like 10 iterations, then you should stop your algorithm, take a smaller neighborhood, and start again.
And how do you fix? How do you set up the maximum number of iteration?
Well, it's you can quite easily do that. Usually, you go for, say, maximum number of 10. But what you will quickly notice is that for most complex systems, such as robots, that have like a, say, a state vector that is larger than 3 variables with quite a lot of nonlinear functions, you'll notice that after, say, 5 iterations, the box is already minus infinity plus infinity. So you can stop as soon as it reaches values that are not meaningful anymore.
Okay. Okay, and last remark about one or your first slide. You said that of course the uncertainty come in system, come from the initial state because it is verification, validation. Okay, for large initial state, you may have uncertain parameters in your dynamic, but of course, I guess that the link with the second part of your presentation, the uncertainties come from the estimate state provided by Kalman filtering.
Well, there are two different things here. The first, I mean, in this slide, I talk very generally about discrete time system and where the uncertainties come from. In the second part, I try, so the part with the Kalman filter, I try to prove that the Kalman filter will converge towards the actual state of the robot.
Yes.
And I am actually verifying the Kalman filter by taking as an uncertainty the initial, I mean, the initial state estimation of the Kalman filter, and also its initial covariance matrix. So we have basically an algorithm like the stability contractor algorithm that checks if a system, say the Kalman filter, it will converge towards a fixed point with initial uncertainties. The uncertainties that are in the Kalman filter are completely hidden by the discrete time system you obtain by transforming a bit your Kalman filter equations. So you do not use like I think I didn't explain it correctly, you do not really use the uncertainties of the Kalman filter. When you talk about uncertainties in Kalman filter, you usually talk about the covariance matrix. We consider the covariance matrix as just a part of our state vector.
Yes and no, because if I understand well, at the end, you prove convergence of the Kalman filter for non-moving robots, saying that, okay? And then you will perform similar work for a moving system, moving robot. But what I said before about this slide, the slide you present at present time, it is that in a general manner, when you have a system, you have a kinematic describing how your system is moving. In this kinematic, you have guidance law, controls, and the input of the controls, the guidance law, the control law, is the output of some observers, Kalman filters. And so some errors come from the fact that the output of the Kalman filter may be with some lag or latencies, errors, and so on. And that perhaps also a source of error, and not only the uncertain parameters. You said as an example mass, the mass of the robot. Okay, so just a remark. Okay.
Oh yeah. So what you mean is that I didn't give all the origins of uncertainties in a system.
No, it's a way to link all what you present, and maybe future result you will obtain with the beginning of your talk, if I understand well. Okay. But okay, I will think more about your stability contractor and the fact that after a couple of iteration. Okay. Thank you for the answer.
Right, thank you.
So, Luc wanted to comment?
Yes, probably one comment, because one point may be confusing is that in the Kalman filter, usually we assume that we have some Gaussian noise and things like this. But here, in this case, we do not care at all of the noise. Auguste just proved the stability. So it means that the covariant matrices and the estimate and so on are seen as a variable of an algorithm. And in fact, it just proves the stability of the system plus the algorithm. So there is, even if the algorithm is false, even if we may have the stability to the true value for the state variable. So I wanted to insist on this because it can be confusing for people who are used of the Kalman filter who assume Gaussianity and things like this. Here, there is nothing like this. We just prove the stability of the closed loop system. There is no meaning of Gaussian. There is no such assumption here.
Therefore, there are some problems. So you may prove that you have no stability, but it is due to the fact that the noise you consider are not Gaussian noise, but defined by intervals.
Yes, I agree, but you can assume what you want. At the end, you have an algorithm, and the algorithm makes you a discrete time system, and this discrete time system may be stable or not. So, of course, if if you had to prove the stability, it means that there is a neighborhood that is small, such that everything. You just prove the stability. There is, probably, you understand what I mean, or probably not, no?
I guess you use the extended Kalman filter equation as a dynamic system. But at the end, that's only that. You don't say it's a Kalman filter. It is some equation coming from the way we write a Kalman filter, something like this, no?
I think you could say at that point it's something like you have some dynamic observer model using some gain adaptation scheme, and the gain adaptation scheme just is motivated by the structure of an extended Kalman filter. And in such a way, if you formulate it like this, you get away of the Gaussian interpretation of noise or estimation covariances, for example. Okay, do we have further questions? I have one further question. We're coming back to the Kalman filter again.
Yes.
And people usually, when they set up a Kalman filter, they have two parameters for tuning. One is the measurement noise covariance, the other one is the process noise. And usually what I tell to everyone is, take the measurement noise as a parameter characteristic from the sensor, use it from the data sheet or perform an experiment and keep it fixed. And the only tuning parameter then should be the process noise covariance. Do you aim at using your approach as some kind of building block in an optimization scheme that allows you to tune the process noise covariance to enhance the robustness?
Well, I didn't think of that application, but that could be, yes, a good idea. Because if you go back to how I chose my parameters,
yes, you did intelligent guessing.
Well, I did intelligent guessing for the initial neighborhood, but for the process and measurement noise, I assume that we can. I mean, I took the measurement noise so that it could correspond to an actual sensor.
Yes, measurement noise could be from the sensor data sheet.
Yeah, absolutely.
Yes, and the gamma alpha, I think, would then be some degree of freedom for an, yes, in an outer loop performed optimization in order to tune it.
Yeah. So you could definitely tune it and at the same time tune the initial neighborhood. Yeah.
Yes, Stefan wants to
yes, therefore I have one complementary question to what Andreas asked. So the question was about process noise and the measurement noise, the ratio, and okay. And what are the cadency, the frequency you use? The measurement frequency, at what time do you receive measurements? How do you fix that?
You can really do whatever you want. The point here is just to transform your here the system is just a Kalman filter algorithm, but if you have a robot that runs continuously in time, and you have a computer that makes your Kalman filter run at a given frequency and a controller at another frequency, then what you can do is take the smallest frequency of them all, discretize your whole hybrid system, and then you obtain a discrete system with a given frequency, and you can just study this discrete system and prove its stability with all the parameters you've been choosing before.
I agree with you, and because it is discrete time, it is easy to tune in the way you want. But if the measurement cadence frequency is it's not the same as the simulation steps, then maybe you will have some difficulties to prove contractance, because you will predict during a long period, and maybe your stability contractor will conclude to no stability. And it is because it is required to perform a simulation during some more steps to have contractance, because generally the stability contractance come from measurements. So
yes.
I don't know if there is not a compromise between all those time steps.
Yes, there
How
definitely is.
how many steps you need to perform with your stability? The maximum number of steps you are able to perform with your stability contractor, and how long you need to wait to receive new measurements, something like this.
This is definitely a degree of freedom on which the designer of the system can play, because the point of our method is to prove stability, but not to prove instability. So if our method with the frequency you chose for your Kalman filter, and the frequency you chose for your simulation, and the frequency you chose for your controller, etc., and all the parameters are correct, then our method may prove stability. But if it doesn't prove stability, that just means that the frequency is not high enough, or the initial neighborhood for the initial position is too big, or so you definitely have lots of degrees of freedom on which you can play to actually prove stability. And if our method cannot conclude, that doesn't mean the system will not be stable. It just means that our method cannot conclude. You have to be more precise in the initial state estimation, or you have too much wrapping effect due to the frequency of your sensors, etc., etc. Yes.
And by the way, it will be perhaps related to the initial condition. Sometimes you have no observability or less observability because the measurement you receive don't provide you. Okay, I guess you would like to say something.
You can finish. It's just for after.
No, it was more brainstorming. I guess in the model you have to add the frequency, you have to deal with observability, and so on. It's just to understand how those tuning parameters fit with the approach Auguste presented.
Yes.
Okay, so I have one question. So Auguste, you have presented the stability contractor, and can you also define an instability contractor that can be used, for instance, to prove the instability of a system?
That's a good question. If I go back to the definition of the stability contractor, that would mean that we could implement stability in the following way. We have to add iteration of the instability contractor. The box must be bigger than the previous one, and then you have instability. Well, actually, do you have instability? No, not necessarily.
No, but I think the same concept maybe could be used, not the same. Probably something, different things have to change. But I think it would be very useful to use this kind of centered form method in order to prove the instability. But
I think it's possible. It's just a backward in time evaluation of the discrete time system model.
Right. Right.
Start with a domain and show that the backward in time evaluation contracts. And then it's the forward in time evaluation is unstable.
Mm-hmm. Yeah, absolutely.
For sure, it's maybe not sufficient, no?
I think maybe we have to think about it a little bit more, but at least that's one possibility of unstable behavior that you can detect with it.
Yeah, I agree. If the backward is stable, but I think maybe it's not sufficient. We'll have to think about this.
Okay, but since we already started with philosophical questions, I also have some philosophical remark. And one is the method that you presented is something, since Stefan already mentioned observability, I think it's a way to show in a constructive way that states are discernible, that states are detectable, and you're performing something like an observer-based verification of the detectability of state variables by evaluating this conversions towards the desired either steady state or the correct state. And from that perspective, I think one could even place your contribution in a much more general framework. And going one step further even is, one of the questions before was, how many time steps do you need for evaluation to show contractors? And I think there's also some relation to the stability proof or observability mappings of discrete time dynamic systems. If your system model is nonlinear, you don't have any a priori bounds how many successive evaluations of the state equations you need in order to show observability. For a linear system model, it's obvious. It's just the number of states that you have to perform. That was something proven by Kalman. But for a nonlinear discrete time system model, in general, there's no upper bound. And that's something that you can even see here in this framework.
Yeah.
Yes, and the last philosophical comment from my perspective is when you place the observer dynamics within the closed loop, that's also something where you could show the closed loop dynamics stability in cases where this separation principle of control and observer design no longer hold. Again, for the nonlinear case there. Because for linear dynamic systems, it's just give to person A the task, design the controller. Person B is designing the observer or the Kalman filter. You're plugging both together and it will work.
Yes.
In the nonlinear case, you may induce unstable behavior just due to the fact, yes, that the interconnection of two stable systems leads to something that is unstable.
Mm-hmm. Absolutely.
Yes, this was the philosophical comments from my point of view. Okay.
Thank you.
Do we have any further questions in the audience? If not, thanks again to all of you for attending this very interesting seminar, and see you again in 2 weeks. The speaker in 2 weeks will be Luc Jolin, and this will be the very last presentation before Christmas. Then we have a short Christmas break, and in the middle of January, we'll continue again. Have a nice Friday afternoon, evening, and enjoy the weekend.
Okay.
Thank you.